Hi everyone, welcome to the Chem 115 Exam 3 review session. I'm basically going to do the same thing that I did for the Exam 2 review session, that is go through the past exam. I'm going to be using the one from spring 2018. Just a few reminders about the upcoming exam on Blackboard for this semester. That's going to be held on Monday, April 13th. It's going to be open for you to access at 3 p.m. and that is going to go until 11:59 p.m. on the 13th. You'll have a 90-minute window within that time frame to complete the exam. So make sure you start before 10:30 if you want to have your full 90 minutes, because the exam will become unavailable at 11:59 on Monday. So as I said, I'll be using the exam from spring 2018. This exam here, so this is the one that is posted on Blackboard currently with the answer key. So I will just get into it. Starting on number 1, how many lone pairs are on the best Lewis structure for the molecule CS2? So what we'll want to do first is draw the Lewis structure for CS2, and we can start by first drawing the electron dot structures for each of the atoms that are involved in that molecule. So that would be 2 sulfurs and 1 carbon. Each of the sulfurs have 6 electrons and the carbon has 4 electrons. If you see on each of the sulfurs, they each have 2 single electrons and carbon has 4 single electrons. So we can make a double bond between each of the sulfurs and the carbon with each of the lone electrons from sulfur and 2 of the lone electrons from carbon. And do the same thing for the second sulfur, so we can make a double bond with each sulfur to the central carbon, and that leaves us with 2 lone pairs on each of the double bonded sulfurs. So just count those up. That gives us 4 lone pairs, so there our answer is E, that it has 4 lone pairs on the best Lewis structure for the CS2 molecule. Moving to number 2, it asks which of the following bonds is the most polar. Here we see each of the different halogens and then hydrogen, so HI, HCl, HF, HH, and HBr. So you don't necessarily need to know the exact electronegativities of each of these atoms to know which is the most polar, because polarity is based on difference in electronegativity. As long as you know kind of a rough gauge of the different electronegativity values, that fluorine is the most electronegative, and then it decreases as you go down that group, and then that hydrogen is even lower than iodine. If you know some kind of rough values, you can predict generally what the difference in electronegativity is going to be between the 2 atoms that are involved in the bond, and that is how you determine the polarity of each bond. So if we just take these rough values that I've written down here, and again the general trend is as you go up the group, it's going to become more electronegative. So subtracting the electronegativity of hydrogen from each of the halogens here, we have 2.5 minus 2, 3.5 minus 2, 4 minus 2, 2 minus 2, and 3 minus 2. So in each of those cases, if we do the math, we get 0.5, 1.5, 2, 0, and 1. So this one is 0 here. That's the one between hydrogen and hydrogen. There's no electronegativity difference because it is the same atom, and the one with the greatest electronegativity difference is 2 here. So that's between fluorine and hydrogen. That makes sense. Fluorine's the most electronegative. Hydrogen's the least electronegative of our group here. So our answer there is going to be C. HF is the most polar bond, which again is the greatest difference in electronegativity. So number 3, which of these compounds violates the octet rule and is an allowed violation? So first we need to determine which of these molecules do violate the octet rule. So the easiest way to do that would be to just draw each of these molecules. So NH3 has a central nitrogen, 3 hydrogens, and then a lone pair. Phosphine, pH3, is a corresponding molecule to ammonia here. Phosphorus, again, is a central atom. It's got 3 hydrogens and a lone pair. SF4, this one's a little bit tricky. Again, you may want to look at the Lewis electron dot structure just for the sulfur atom. You see that it has 6 electrons, only 2 single electrons, but 4 fluorine atoms. So each fluorine is going to need to make a single bond with this sulfur, so we'll have to use one of these lone pairs in order to do that. So again, we'll draw the sulfur as our central atom. We'll draw each of the 4 fluorines, again splitting one of these lone pairs, so that'll leave us with 1 lone pair. Carbon monoxide, so that's the carbon with a triple bond to oxygen, where each have a lone pair. And then BF4 minus, so boron normally has 3 bonds, but in this case it has 4, so 1 extra bond to fluorine. And that's where the minus charge comes in, since it normally has 3 bonds. Having these extra electrons around that boron give the boron a negative charge. So which of these violates the octet rule? So the octet rule is that each atom, other than hydrogen, likes to have 8 bonds in its valence shell. So each bond is worth 2 and the lone pair is worth 2, so this has 8. Phosphine, the phosphorus has 8. Here the sulfur has 4 bonds, so that's 8, and then there's a lone pair, so that gives us 10 electrons around sulfur, so that does violate the octet rule. And then for each of these 2 atoms, they each have 8, and then boron has 4 bonds, so it also has 8. So out of these 5 molecules, SF4 is the only one that does violate the octet rule. And it is an allowed violation because sulfur can, it has an extra P3 orbitals that it can use. So if we look at our periodic table, we see that sulfur is in the 3rd period, so when it has P3 orbitals, it can expand somewhat and have additional bonds. So this is an allowed violation, so the answer there is going to be C. Number 4 wants to know which of the compounds shown below would not be able to form hydrogen bonds with itself. So a hydrogen bond is when hydrogen is bonded to an electronegative atom and then can coordinate with other electronegative atoms. So the only atoms that hydrogen can be connected to and participate in hydrogen bonding are fluorine, oxygen, and nitrogen. So these are the three of the most electronegative atoms. They're also very small, so when you have situations like each of these hydrogens can participate in hydrogen bonding. And the question wants to know which of these molecules could hydrogen bond with itself. So it may be helpful just to draw each of these quickly. So this is methanol. We just saw ammonia in the previous problem, as well as phosphine, hydrogen fluoride, and hydrogen peroxide. So if you see in each of these molecules, the hydrogen here, 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 and here, those can all act as hydrogen bond donors, and each of these electronegative atoms can accept a hydrogen bond. So oxygen, nitrogen, fluorine, and oxygen. And the only one that doesn't have either a fluorine hydrogen, oxygen hydrogen, nitrogen hydrogen bond is phosphine, which only has phosphorus hydrogen bonds. So C there is a correct answer. phosphine would not be able to hydrogen bond with itself. So, moving to number 5, it wants to know what is the strongest type of intermolecular interaction that can occur between propane and water. So there, it's helpful to rule out first a couple of these interactions. So there are no ions in either of these molecules, so we can eliminate A and D, which are both interactions that involve ions. And then we would want to draw propane. So all the bonds here are CH bonds, so this is going to be a nonpolar molecule. So we'll also draw water. So this is a polar molecule with the dipole looking something like that. It can also hydrogen bond, but there are no hydrogen bond acceptors in this nonpolar propane. But this is polar, and it does have a dipole. So one of the possibilities is this is going to have a dipole interaction, and the only possible intermolecular interaction that a nonpolar molecule like propane can do is induce dipole. So since we only have one dipole, we can eliminate dipole-dipole, and since we do have one dipole, we can't induce dipole. Induced dipole is going to be not as strong as dipole-induced dipole. So C here is the correct answer. These two molecules will have induced dipole, or dispersion interactions, but it wants to know what is the strongest type of intermolecular interaction, and that is dipole. Induced dipole is stronger than dispersion, so that's why C is the answer there and not E. Moving to problem number 6, it asks which of the pairs shown below does not match the molecule with its correct molecular shape around the central atom. So here, again, it may be helpful to draw each of these molecules. And remember, we're looking for the molecular shape, not the electron geometry. So if we draw water, ammonia, BF3, C2H4, and C2H2. So we want to know which does not match the molecule with its correct molecular shape around each of these central atoms. So water here has 4 electron groups, 2 of which are bonding groups. So that is going to give it a bent geometry. So that one matches up. Ammonia here has 4 groups again, 3 bonding groups, and 1 lone pair. So that would give it a trigonal pyramidal molecular shape. But here it's saying tetrahedral. It would have a tetrahedral electron geometry, but we want to know the molecular geometry. So this one does not match. I'll just walk you through the rest, but B is going to be our answer here. This one does not match with the molecular shape around the central atom that is listed here. If we move to BF3, there are 3 groups around boron, all 3 of which are bonding groups, so trigonal planar is going to be the correct geometry there. If we look at ethene, so we have 2 carbons double bonded to one another. Either carbon can be taken as the central atom in this case. So we want to look at, let's say, this carbon. There are 3 electron groups. Even though this one is a double bond, that still counts as 3 groups. All 3 are bonding groups, so again, that's going to be trigonal planar, just like it was for the BF3 molecule. Then looking at our final molecule, C2H2, that is acetylene. Again, we can look at either of the two carbons and take that as central. So if we look at this one, we see it as two bonding groups. Again, even though this one is a triple bond, that counts as one electron group. Both are bonding groups, so that is a linear molecular shape, so that one matches as well. So again, just to reiterate, the ammonia molecule here has 4 electron groups, 3 of which are bonding groups, so that's going to give it a trigonal pyramidal geometry, not tetrahedral geometry. So, moving to number 7, it asks which of the following molecules is not correctly paired with the hybridization of its central atom. So this problem is going to be similar to the previous problem, but it wants to know now about the hybridization of the central atom. So again, it may be helpful to draw each of these molecules just to see what it looks like around each of the central atoms. So SiH4 looks like that. Then we have BF3 again. NH3, so ammonia. Ethene. And water. So starting with SiH4, we see that there are 4 groups around that central silicon. So when there are 4 groups, that's going to correspond to an sp3 hybridization, because if you have 1 s orbital and 3 p orbitals, that's going to be 4 sp3 orbitals, which corresponds to 4 groups. So this one is correctly paired. Moving to BF3, there are 3 groups around the boron, so that's going to correspond to an sp2 hybridization, for the same reason that this was sp3. When you have 1 s orbital and 2 p orbitals, they make 3 sp2 orbitals, so that corresponds to 3 groups, which this boron does have, so that matches there as well. Looking at nitrogen, so there are 4 groups here. So 3 bonding groups and 1 lone pair, so that would correspond to an sp3 hybridization. There were 4 groups in ammonia, there were 4 groups in the SiH4, so both are going to be sp3. That does not match with what we see listed over here. Just to round out the remaining answer choices in our problem here, again for ethene we can look at either of these central carbons. They have 3 groups. When you have 3 groups, so it's going to correspond to an sp2. Again, there would be 3 sp2 orbitals, 1 s and 2 p orbitals hybridized to make 3 sp2 orbitals. That gives you 3 groups. So that's what we see around both of these central carbons, so that does match with what we're shown here. And then finally, water. There are 4 groups, so that's going to correspond to an sp3 hybridization, so that does match. So again, ammonia is our answer choice. It's not correctly paired with the hybridization of its central atom, which is nitrogen here. Moving to problem number 8, it asks what is the molecular formula for the following skeletal structure. So the skeletal structure is drawn just with the carbon backbone without any of the hydrogens drawn in. So if we just redraw this molecule with the carbons and the hydrogens, that may make it a little bit easier. So this is the carbon backbone that we see here, and if we add in each of our hydrogens so that each carbon has 4 bonds, we'll put 1 hydrogen on each of the carbons on this side of this aromatic ring, because each of these carbons, 1, 2, 3, 4, already have 3 bonds. These carbons that are in the bridge here already have 4 bonds, so they don't need any hydrogens. And then the 4 carbons on this side of our carbon backbone each only have 2 bonds, so we'll give each of them 2 hydrogens. So then all we'll need to do is count up the carbons and count up the hydrogens. So we can eliminate some answer choices after we count up each one. So there are I'll just label them as we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So we can eliminate C and A because they each show 8 carbons. But then if we count the number of hydrogens, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that eliminates B and E. That leaves us with D. We see here that we have 10 carbons and 12 hydrogens. So that matches with answer choice D. So that is the molecular formula given this skeletal structure. So moving to number 9, it refers to the skeletal structure in the previous problem. So I won't redraw that just yet, but know that we are going to be using that same skeletal structure. So maybe I'll just draw it small up here. So that's the skeletal structure that we're going to be using in the previous problem, question 8. And this problem wants to know how many sigma and how many pi bonds are shown in this structure here. So a pi bond happens anytime there are multiple bonds, and a sigma bond is present in multiple bonds as well as single bonds. So when you have a single bond, you have a sigma bond, and when you have a pi bond, you have a double bond. So single bonds have 1 sigma bond, double bonds have 1 pi bond and 1 sigma bond. So if we redraw this structure here, so just drawing the carbon backbone here, so I'll fill in where each of our hydrogens were in the previous drawing. So if you remember, the formula for this one was C10H12. That's what I've drawn here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So then I can go in and add in our sigma and pi bonds. So I'll do the sigma bonds first, because that's going to be any place there's a single or a double bond. So that'll be, I'll just count them as I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that'll be 23 sigma bonds. And then if we look at our skeletal structure up here, we see we have 3 double bonds, so that would correspond to a pi bond. So if I add those in, that'll be 1, 2, 3. So that's 3 pi bonds. That matches with choice E over here. So after having counted the 23 sigma bonds, we really could have stopped because that's the only answer choice with 23 sigma bonds, but just to verify, we added in our 3 pi bonds that are present in each of our double bonds from our skeletal structure. So 23 sigma bonds and 3 pi bonds are what are shown in this representation here. Moving to number 10, it asks which of these compounds is not an isomer of the others. So here we see several different compounds. A couple different ways you could go about this problem. One would be to just count up all the carbons and hydrogens that are present in each of these isomers, or potential isomers. So in order to do that most easily, we can add in the hydrogens that aren't shown on each of these structures. Just remembering that each carbon wants 4 bonds, so you can fill in the remaining missing bonds with hydrogens in each case here. So I'm just going to draw wedges where the rest of these should go, just to kind of conserve a little bit of space, but each of these lines corresponds to a hydrogen bond to carbon. So if we count up each of the carbons and hydrogens for each of these structures, we see that we have 1, 2, 3, 4, 5, 6 carbons in A, 1, 2, 3, 4, 5, 6 carbons in B, 1, 2, 3, 4, 5, 6 carbons in C, 1, 2, 3, 4, 5, 6 carbons in D, and 1, 2, 3, 4, 5, 6 carbons in E. So then we'll need to count up the number of hydrogens as well. So we have 2, 4, 6, 8, 10 in A. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens in B. In C we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In D we have 2, 4, 6, 8, and 10. And then in E here we have 2, 4, 6, 8, 10 hydrogens. So you can see that one of these is different. Choice B here has 6 carbons and 8 hydrogens, where all the rest have 10 hydrogens. So B is going to be our answer choice there. Another way you can do this is by looking at the unsaturations. So an unsaturation is when you have a multiple bond or ring. So looking at A, there were 2 rings, so I'll make a third row here for unsaturations. So there were 2 unsaturations in A. B was a triple bond and a double bond. So a triple bond has 2 unsaturations, a double bond has 1, so B had 3 unsaturations. C had 2 double bonds, so that's 1 unsaturation each. D was cyclohexene, so it had 1 ring and 1 double bond, so 1 unsaturation for each of those gives us 2. And similar for E, we had 1 ring, 1 double bond, 1 unsaturation for each, giving us 2 unsaturations total. So again, you can see that B is different here. It has 3 unsaturations. The rest of the molecules had 2 unsaturations. So that extra unsaturation accounts for the 2 less hydrogens as well. So that makes B not an isomer with the rest of the molecules that you see here. Number 11 wants to know which of these compounds shown is a ketone. So a ketone will have the general formula like this. So it'll have a central carbon double bonded to a carbon, and then a carbon singly bonded to that central carbon on either side of this carbonyl here. So if we look at each of these structures, we see that there's not a carbonyl, so no CO double bond in A, so we can pretty much eliminate that one right off the bat. Here we have a carbonyl, so CO double bond. On one side we have a carbon, but on the other side we have an oxygen, so we can eliminate that one. Answer choice C. We have our CO double bond here, and then on both sides we do have a carbon, so that is a ketone. And then looking at the final one here, our CO double bond, but it has a carbon on this side and an oxygen on this side, so we can eliminate that one as well. So this is an ether, this is a carboxylic acid, this is a ketone, and this is an ester here. So we want ketone, so our answer there is going to be C. So number 12 wants to know which of these structures does not exhibit resonance. So resonance is the ability of a molecule to kind of reposition electrons within the structure. So molecules that can do that typically have either charges or multiple bonds or both. So we'll look at each of these here. I'll just redraw some of these a little bit bigger. So looking at the first one, we have this structure. So we have a charge, a negative charge, and multiple bond. So those are both good indicators, especially since they're right next to each other, that this molecule is going to exhibit resonance. So that's what we're looking for. So this negative charge comes from the fact that this oxygen has a single bond, which means it has 3 lone pairs, which is more electrons around the oxygen than it would normally have. So hence the lone charge, or the negative charge, because of the extra lone pair. This oxygen is neutral. It has its normal amount, 2 lone pairs. So one of these lone pairs can form a double bond here, and the electrons from this double bond can go up into that oxygen. So that'll give us a resonance structure, where now this oxygen has 3 lone pairs, so it's negatively charged, and this oxygen has 2 lone pairs and a double bond, since one of these lone pairs formed the double bond, and this one of these 2 bonds from the double bond went up to give us this 3rd lone pair. So that's what resonance is. So this one does exhibit resonance. We can't do something like that for the molecule shown in B. We have 2 lone pairs around our oxygen. There's no charges, and there's not really anywhere for these electrons to go. So that one does not exhibit resonance. If we look at C, alternating single and double bonds is a good place to have some resonance structures. So here we have double, single, double, and single bonds. The resonance structure of this type of aromatic system inverts the ordering of the double and single bonds. So if we draw the resonance structure, this double bond is going to move here, this one will move there, and this one will move there. So we just switch which bonds are double and single. So this double bond moved here, this one moved here, and this one moved there. So that one does have a resonance structure. And then looking at D here, which is ozone. So O3. This oxygen has 2 lone pairs, this one has a single lone pair, and this one has 3 lone pairs. So neutral oxygen has 2 lone pairs, positively charged oxygen has 1 lone pair and 3 bonds, and the negatively charged oxygen has 3 lone pairs. So this is a similar situation to what we saw in our first example here. This lone pair from the oxygen with the negative charge can form a double bond here, and then this double bond will donate those 2 electrons to this oxygen, giving it 3 lone pairs. So this oxygen now has 3 lone pairs, so that means it has just 1 bond because these 2 electrons are now in a 3rd lone pair. The central oxygen still has 1 lone pair in its positive charge because this became a double bond when these lone pair electrons formed a 2nd bond here, leaving this one with 2 lone pairs. So these 2 are resonant structures of one another. So D also is able to exhibit resonance, so that means that B is our answer. It's the only molecule of these 4 that is unable to exhibit resonance. So, number 13 wants to know which of the following molecules here is named incorrectly. So, the best place to start here would be with each of these prefixes that indicate how many carbon atoms should be present in each of these structures. So, if you remember the ordering, so these are the prefixes for the first 9 hydrocarbon molecules. So if it's an alkane, like we see here, where there's all carbon, hydrogens, and single bonds, that'd be methane. So that's 1 carbon. So ethane would be 2 carbons, propane is 3, butane 4, pentane 5. So here is pentane. We see that it has 5 carbons. Hexane is 6, heptane is 7, octane is 8, and nonane is 9. So these are just the prefixes. It depends what type of hydrocarbon it is. So only single bonds are alkanes. So it would have the ane suffix there with the meth prefix. Alkenes have a double bond somewhere in them. So ethene, which we've seen several times previously in other questions in the exam, have just a carbon-carbon double bond, and the rest are hydrogen, so they have a double bond. There's 2 carbons, which is what we see here, and then the rest are carbon-hydrogen single bonds. There's also alkynes, so those have a triple bond somewhere. So propyne would be the 3 carbon hydrocarbon with a triple bond. So this is 2 carbons, there's the 3rd carbon, and the rest of the bonds here would be to hydrogen. So one other thing would be if you have the cyclo prefix, that goes out in front. So an example here is cyclopentane, which we see here. It's cyclic, and it has 5 carbons, and it is an alkane. So there's only single bonds between the carbons. So we'll look first at the prefixes for each. So here we have pentane, so that should be 5 carbons. Cyclopentane should also have 5 carbons. Cycloheptene should have 7 carbons. Octane should have 8 carbons. And butane should have 4 carbons. And that's just going with each of the prefixes that we see here. So the cyclopentane, the cyclo prefix indicates that this is a cyclic molecule. Cycloheptene, it's cyclic and it has this alkene. Octane is just an straight chain alkane. And butane has the triple bond here because it's an alkyne. So if we count each of the carbons in these molecules, 1, 2, 3, 4, 5, so that matches. 1, 2, 3, 4, 5, that matches as well. 1, 2, 3, 4, 5, 6, 7, that matches. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that does not match. This is actually nonane. So that's going to be our answer for this problem. But just to finish it up, butane has 4 carbons, and that's what we predicted here. So this is actually nonane because octane would have only 8 carbons. So octane would look like that. This is nonane, it has 1 additional carbon. And that was just basing that on the generic prefixes for hydrocarbon molecules. Moving to number 14, we're asked to calculate the number of repeat units in a sample of polylactic acid with a polymer molecular mass of 30,000 grams per mole. The lactic acid monomer is shown below. So we'll need to first calculate the molecular mass of this lactic acid here. So to do that, we can use our periodic table values. So we have 1, 2, 3 carbons, 1, 2, 3 oxygens, and 1, 2, 3, 4, 5, 6 hydrogens. We'll look at the values for each of those on our periodic table. So hydrogen is 1.008 AMU, carbon is 12.01 AMU, and oxygen is 16.00 AMU. So if we calculate each of those, for carbon we're going to get a value of 36.03. 3 oxygens will give us 48, and 6 hydrogens will give us 6.048. So the molar mass is just going to be the sum of each of those, so that's going to be 90.078. So when we look at this monomer here, we should be able to see that it is going to form a condensation polymer. The other option would be addition polymer, but those typically always involve carbon-carbon double bonds. We don't see that in here, so we can infer that this is going to go through a condensation polymerization, which will cause a small molecule to condense out of the polymer from the monomer units. So that's why it's called the condensation polymerization. It's condensing out some small molecule. So if we draw just a short repeat of this particular polymer, it's going to look something like this. So here I just drew 2 repeat units. So we can see that the small molecule that we lost going from here to here is going to be water. So in the 2 units here, the 2 repeat units, there are 4 oxygens. In the monomer there were 3 oxygens, so there should be 6 oxygens if the full monomer were conserved during the polymerization. We see that there are 1 fewer oxygens per unit, and also 2 fewer hydrogens. So if we count up 6 hydrogens that we got here, there should be 12 hydrogens that we see if the whole molecule was conserved, but we see that there are 1, 2, 3, 4, 5, 6, 7, 8. So we lost 4 hydrogens and we lost 2 oxygens. per monomer. So that's how we came up with that we're losing an H2O, or a water molecule. So we need to subtract that mass from the molecular mass that we calculated for lactic acid. So that would give us 2 hydrogens, 1 oxygen. So 2 hydrogens are 2.016 AMU, and 1 oxygen is 16.00 AMU. Take the sum of those is 18.016. So subtracting 18.016 from 90.078, we get the molecular mass of the repeat unit is 72.062. So what we want to do now is divide 30,000 grams per mole by the molecular mass of the repeat unit. So when we do that, we get that that is equal to 416.3. So that's pretty close to answer choice B. You can't have a partial repeat unit, so you're going to round this up to 417. So that matches with answer choice B here. Alright, moving to number 15, it asks which monomer created the polymer shown below. So this one pretty clearly came from an addition polymerization. So we can identify the repeat units here. So in each of these we have 2 carbons. Attached to this carbon there are 2 chlorines, and attached to this carbon there are 2 hydrogens. So remember then, in addition polymerization, the starting materials are going to be alkenes, which are double bonds. So when you have multiple double bonds next to each other, the double bond is going to form a single bond with the adjacent double bond, so that gives you the single bonded backbone from double bonded monomer units. So if we add the double bond in between the 2 carbons of the repeat unit here, we see that we have 2 chlorines on one side of the double bond and 2 hydrogens on the other side of the double bond. So that matches with answer choice C, because both of the chlorines are attached to a single carbon. Here there's 2 chlorines, but they're on 2 different carbons. We want the one where both chlorines are on the same carbon and both hydrogens are on the same carbon. So that is choice C here. Alright, number 16 asks which of these molecules is the best match with the IR spectrum shown. So looking at the IR spectrum here, we see that there are 2 peaks that are identified. This sharp peak at 1721, and this kind of broadish round peak at 2971. So we can look at our IR frequency table here that's part of our supporting information. So things in the 1721 range are going to be things like a CO double bond, CN double bond, or CC double bond, so carbon double bonded to some atom. So a couple possibilities here: C double bond O, C double bond N, or C double bond C. And then if we look at the other peak, 2971, going back to our table. So that's going to be right about here. So that is going to be OH or NH stretch or CH stretch. So just from my experience with IR, CH stretch is going to be kind of a sharp peak around 3000, where the OH and NH stretches are going to be more of a broad, stronger stretching frequency. So that's what we see here. If it were just a CH stretch that does come around that same positioning, it would look just like this sharp part that we see here, but it would only extend down to about this height. But there's this broader kind of background peak that's going to come from either an OH or NH stretch. So since this IR spectrum has both of these stretches, we want to look for a molecule which has both of those kind of bond systems in them. So an OH or an NH, A only has carbon and carbon-hydrogen bonds, so that one's out. B has nitrogen, but it only has nitrogen bonded to carbon, so that one is out. C does have an OH, so that one does match up. And then D also has an OH. So far, this broad OH or NH peak, we now know that it's an OH, could be from either C or D. But we also see that there's this sharp peak at 1721. That's going to come from carbon double bonded to oxygen, nitrogen, or carbon. So looking at each of these two, we see that only C has a double bond between carbon and oxygen, where this propanol molecule does not have any double bonds. So here our answer is going to be this carboxylic acid, which has an OH corresponding to this broad stretching region here in the IR spectrum, and this C double bond O, which corresponds to this sharp peak around 1721. So C here matches best with this shown spectrum. Alright, moving to number 17, it asks what is the energy of the photon contributing to the peak at 2971. So in the previous problem, the peak at 2971, it's not important at this point what that peak actually is. We just need to know what wave number that peak had. So that is 2971, and we want to know the energy of that photon. So in order to calculate the energy of the photon, we can look at our equation sheet. We see that there's really only one equation that is going to give us energy, and that is this one here. So E equals h nu, or E equals hc over lambda. So here we would need to know the frequency, and here we would need to know the wavelength. So I'm going to calculate it using E equals hc over lambda. So we know h and c from the constants that are given to us here on our useful information sheet. So h is Planck's constant, so that's 6.626 times 10 to the negative 34 joules times seconds, and we're going to multiply that times c, which is 3 times 10 to the 8th, and that is meters per second. So when we multiply those two values together, that's going to give us 1.9878 times 10 to the negative 25th, and then here the seconds cancel. So joules times meters. So that means our energy is equal to that number over our wavelength. And we want the answer in joules, so we need our lambda here, the wavelength, to be in meters, but we have our wave number in inverse centimeters. So we'll need to convert this number into meters. So if we look at our wave number, 2971, 1 over centimeters, we can divide 1 by this value, and that is going to give us 3.366 times 10 to the negative 4th centimeters. Since we took the inverse of this number, we also took the inverse of the units, so instead of inverse centimeters, we now have just regular centimeters. And then we want to convert that to meters, so that cancels the meters from our units here in the energy equation. So to do that, we will multiply times the conversion factor. So that would be 1 meter is equal to 100 centimeters. So we divide this number by 100. That gives us 3.366 times 10 to the negative 6 meters. So when we plug that value in here, there the meters are going to cancel, so we divide 1.9878 times 10 to the negative 25th joules meters divided by 3.366 times 10 to the negative 6 meters. That is going to give us 5.9055 times 10 to the negative 20th joules. So 10 to the negative 20th matches with this. That's really the only one that's anywhere close to that. And if we round this number, 5.91 times 10 to the negative 20th joules. So our answer here is A. Alright, moving on to number 18. It says in lab, we mix polyvinyl alcohol with borax. The reaction between the polyvinyl alcohol and the borax is an example of which of these answer choices here. So, these two are different polymerization reactions. So, condensation polymerization and addition polymerization we saw examples of earlier in problems in the exam. So you actually formed the polyvinyl alcohol using addition polymerization. So that is vinyl alcohol. When you have multiple vinyl alcohols, you have to initiate the polymerization. So that typically adds something over here that breaks this bond, which causes it to form a bond with this carbon, which then initiates the chain reaction to form the polyvinyl alcohol polymer. So that covers initiation, which is what you need to do in order to initiate the polymerization. Addition polymerization is when multiple alkene monomers form single bonds between them to form an addition polymer, like polyvinyl alcohol. So that's not what's happening when we mix borax with the already formed polymer. And then condensation polymerization, a small molecule comes out of the polymerization. So this was a polymerization that we saw up here. No small molecule came out of it, and that's not even the step that we're concerned with. We're concerned with the mixing of the borax with this preformed polyvinyl alcohol. So we can rule out A as well, but just so we can kind of see what B means, that is cross-linking. So we're going to have two individual polymers here, both of which are our polyvinyl alcohols. So if we have that kind of PVA polymer chain, and we have a borax somewhere in the middle there, so I'll just start drawing borax. So each of the borons that are not those two, so you have two borons that are negatively charged, two borons that are neutral. It's because you have Na2 B4 and then O 1, 2, 3, 4, 5, 6, 7, and then H 1, 2, 3, 4. So that is borax. And if we have a second molecule of polyvinyl alcohol down here, so we'll use the same length, 3 repeat units of this PVA and this PVA. So these are two separate polymers. The borax is able to hydrogen bond with OHs on either side, so you have donors and acceptors in both molecules. So the central borax hydrogen bonds with the PVAs on both sides, effectively cross-linking this PVA polymer with this PVA polymer. The borax in the middle here acting as the kind of bridge where it hydrogen bonds between both the polymers, effectively cross-linking them. So that's what happens when you mix the polyvinyl alcohol with the borax. It is a cross-linking. Alright, moving to number 19, it asks which of the following molecules is polar. So probably the easiest thing to do to determine that would be to first draw each of those molecules. So number 1 is SCl4, so there's 4 Cl's, 1 S. If you draw the electron dot structure for each of those, chlorine has 1 single electron in its electron dot structure. Sulfur has 2 single electrons, 2 electron pairs, but we need to form 4 bonds with chlorine. So again, we're going to have to break up one of those pairs of electrons like we did for SF4 that we saw earlier, leaving us with 1 lone pair. So sulfur will be our central atom. We'll form 2 bonds to chlorine with each of the lone electrons. We'll break up one of the pairs of electrons to form 2 more bonds to chlorine, and that will leave us with a lone pair on sulfur. So that will actually make the molecule asymmetrical, and that will give it a dipole in the direction of the chlorines, because chlorine is more electronegative than sulfur. So each individual bond dipole will be towards the chlorines. The horizontal component of the bond dipoles will cancel, but the vertical components here of these two are in the same direction. Again, the horizontal components will cancel, but that'll give the molecule a molecular dipole overall pointed in that direction. So 1 is a polar molecule. So we'll move on to number 2 here. We have now 5 chlorines. So again, each chlorine has 3 pairs of electrons, 1 single electron, and each phosphorus, there's 1 phosphorus, has a pair of electrons and 3 single electrons. So we need to form 5 bonds between chlorines and phosphorus. So each chlorine single electron is going to form a bond with each of the 5 phosphorus electrons. So this is going to be another octet violation, but it is an allowed violation because, again, phosphorus has access to lower orbitals and can expand its octet somewhat. So we have 1 bond to each of the chlorines from phosphorus, and I'm drawing these two towards us and slightly away from us. These 2 chlorines are axial, and these 3 chlorines are equatorial. So the bond dipoles of these 2 axial phosphorus chlorine bonds cancel because they're directly opposite one another, and then the bond dipoles of each of these phosphorus chlorine bonds, the 3 combined, directly cancel one another out. So overall there is no molecular dipole here, so this is not a polar molecule. So this was 1, this was 2, and we'll do number 3, which is SO2. So we have 2 oxygens and 1 sulfur. So since oxygen and sulfur are in the same group, they have the same electron configuration, 2 pairs of electrons, 2 single electrons, but in this molecule we have 2 oxygens and 1 sulfur. So we are going to have to use each of these lone electrons from oxygen to form a double bond with the sulfur. Oxygen is not far enough down in the periodic table to be able to expand its octet, so each of the single electrons will be the only ones that can be paired with sulfur. So if we draw oxygen double bonded to sulfur, that uses 2 of sulfur's electrons, leaving oxygen with 2 lone pairs. So if we draw a second double bond to an oxygen, it uses 2 more of sulfur's electrons and leaves this oxygen with 2 lone pairs. So we've used 4 of sulfur's 6 electrons, so that leaves it with 2 electrons, meaning that it has 1 lone pair. So this again makes sulfur not a completely symmetrical molecule, because if we look at the bond dipoles, they're pointed towards each oxygen, since oxygen is more electronegative than sulfur. So that's going to give this molecule an overall molecular dipole in this direction. So this is a polar molecule as well. So looking at our answer choices, 1 and 3 are polar, so that is going to correspond to answer choice C here. Just 2 and 3, 1 and 3, sorry, are polar, and 2 is a nonpolar molecule. So moving to the final problem here. Shown below is the structure for p-cumaric acid. Calculate the number of moles of p-cumaric acid in 10 milligrams of the solid p-cumaric acid. So in order to calculate the number of moles, we're first going to need to calculate the molar mass of this molecule. So to make it a little bit easier to determine what the molar mass is, I'll add in the implied hydrogens here, just so we can calculate the formula just a little bit easier. So if we count up each of the atoms, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. We have 1, 2, 3 oxygens. And then we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Taking the atomic masses for each of those from our periodic table that we get in our supplementary information, we can see that each of those carbons weighs 12.01 AMU, each oxygen is 16.00, each hydrogen is 1.008. So when we do the math for each of those, the 9 carbons are 108.09, the 3 oxygens are 48.00, and the 8 hydrogens are 8.064. So when we add each of those together, we get a total of 164.154, and that's going to be grams per mole. So we have grams per mole. We need to calculate how many moles 10 milligram sample of this material is. So we're given it in milligrams. So we'll want to convert milligrams to grams. So we can use the conversion factor. 1 gram is equal to 1,000 milligrams. So there, the milligrams are going to cancel. We'll divide 10 by 1,000. And that will give us 0.01 grams. So now that we know the mass of our sample in grams, we can divide that mass by the molar mass, and that will give us the number of moles. So if we take this number, divide it by our molar mass, so molecular weight, 164.154 grams per mole. There the grams are going to cancel, and that will give us 6.0918 times 10 to the negative 5 moles. So each of these looks like it's rounded to 2 decimals. So 6.09 times 10 to the negative 5 moles. That matches exactly with B here. Alright, so that was all of the problems from the Spring 2018 Exam 3. So again, that is posted on Blackboard currently. This is the end of the review session, but just as a follow-up, if anyone has any additional questions, I will be hosting a live Q&A. So that is going to be on Piazza. So that's the website that acts as like a forum. I'm going to be doing a live Q&A on that to answer any questions about any of the problems that you just saw or any other questions you may have regarding the upcoming Exam 3. And that is going to be on Sunday, April 12th. From 12 p.m., so noon, to 1 p.m. So this is going to be a second part, kind of our review session to provide any answers to questions you may have in lieu of doing the in-person review session. It will be text-based. But I figured it would be a better way than having people try to talk over one another in some sort of video Q&A session. So this way I can see everyone's questions, and then you can upvote questions, so the most popular questions I can answer first and then work my way down the list. So again, that's going to be on Sunday. So approximately 36 hours after this review session is posted online, I will be hosting the live Q&A. So hope to see you there.